Hi, everyone. I'm so excited to welcome our next speakers, Dhruv and Devi, to the stage. They split time between Facebook and Georgia Tech, and Devi was included in Forbes' list of 20 incredible women advancing AI research. So please join me in welcoming Dhruv and Devi.
Hi, everyone. My name is Devi Parikh.
And I'm Dhruv Batra.
And we're both research scientists at Facebook AI Research and faculty at Georgia Tech. And so what we're going to do today is the following. I'm going to start by telling you a little bit about Facebook AI Research, or FAIR in general, its mission and its philosophy. And I'll give you a glimpse of a few different projects going on in different subfields of AI, like vision, in language, and reasoning. And then Dhruv, who also happens to be my spouse, will talk about some projects that we've been working on at the intersection of all three. And then I'll finally come back and wrap up with some comments on bringing humans and AI closer together. All right, so let's get started. So Facebook AI Research, or FAIR's mission, is to advance the state-of-the-art in AI through open research for the benefit of all. And so let me unpack this a little bit for you so I can emphasize certain values that are core to how FAIR operates. So the first, and perhaps an obvious one, is the emphasis around AI. So a lot of the work that FAIR does revolves around artificial intelligence. And in particular, FAIR focuses on advancing the state-of-the-art in AI. And so what this means is that we focus on basic fundamental research for longer-term impact on the science and engineering in AI. And so the way in which we can try and track progress towards this longer-term goal is by evaluating our technology on well-established existing benchmarks in the research community, or introducing new benchmarks as we try and focus on newer and newer challenges moving forward. And because we are at the cutting edge of AI research, a lot of the work that we do often wins Best Paper awards at academic and research conferences. And so the way in which we try and advance the state-of-the-art in AI is by conducting open research. And so, for example, we open source a lot of the technology that we build. We publish our results and technology at academic research conferences. And we have very close collaborations with universities. And so this is through internship programs where graduate students can come and spend time at FAIR, visiting scientist positions where faculty, other academics can come spend time at FAIR, and deeper collaborations through positions like Dhruv and I have, where we are splitting time between FAIR and Georgia Tech. And so this, for instance, is our group at Georgia Tech, and a lot of the projects that Dhruv will talk about were led by some of the students that you see here. And the overall philosophy being that problems in AI are challenging, and if we want to make fast but effective and thoughtful progress, it has to be in collaboration with the rest of the research community, and that can happen only through open research. All right, so with that, hopefully you have a sense for how FAIR is situated and what philosophy and mission it has. And what I'll do now is give you a glimpse of a few different projects going on in different subfields of AI, like vision, language, and reasoning. And so let me start by computer vision. And so this recent project, DensePose, what we have are state-of-the-art algorithms and models that can accurately track the poses of people in videos in the wild, like you see here. And so you can imagine applications around augmented reality or assistive technology for the elderly, and so on. Here's another example. FAIR has state-of-the-art object detectors and segmentation algorithms, where given a consumer photo like the one you see here, we can accurately draw bounding boxes around individual objects and segment their shapes out, for example, around wine glasses and chairs and tables and forks and plates and so on. And again, the kinds of applications where this might be useful is aiding visually impaired users, augmented reality, autonomous driving, or sort of any application that requires an understanding of the visual surroundings of the agent that you have. And all of these object detection models have been open sourced in this nice repository called Detectron that has tens of models, one of which I showed you earlier. And what's nice is that these models include models that won Best Paper awards at top-tier conferences just about 6 months ago. And so this is all publicly available for you to use. So that's a little bit of a glimpse in the computer vision space. In the natural language processing space, I want to talk about two themes. The first one is around multi and cross-lingual technology. So FAIR has open sourced these fast and really accurate machine translation models. So if you wanted to translate from one language to the other, you could use these. FAIR has also open sourced classifiers and embeddings in 294 different languages. So if you need to reason about anything beyond just English, this can be a very valuable resource. And finally, FAIR has also open sourced models that let you embed 30 different languages all in a common space, all aligned. And so again, for cross-lingual applications, this can be quite useful. And so that's in the cross-lingual, multilingual space. The other theme I want to talk about is around dialogue agents. And so FAIR has been doing quite a bit of work in terms of papers and data sets around whether it's chatbots, where you're trying to build dialogue agents that are socially pleasant to interact with, or goal-driven assistive bots, where the bot is trying to help a user get a certain task done. And so in addition to this, these sort of papers and data sets that FAIR puts out, FAIR often also helps organize challenges like the one you see here on conversational intelligence to help sort of coordinate research efforts in the broader community. FAIR has also released this unified platform for dialogue research where different research groups can put in their data sets, their models, so that different models can be evaluated across a wide range of tasks, and people can train on different data sets on multiple sources of information. And again, this helps sort of bootstrap research within the community at large. And one other interesting thing that FAIR has done in this space is we put out a call for proposals where academic groups could write up proposals on what kind of research they'd like to work on in the dialogue space, where they can take advantage of this platform, and FAIR funded some of those groups at many universities. And this, again, like many other things, is open source for you to check out. All right, and the last thing I want to talk about before I hand it over to Dhruv is some work that FAIR is doing in the reasoning space. And one area that's of particular interest is real-time strategy games. And so what FAIR has done is we've integrated Torch with StarCraft, and we've collected and publicly released this data set that others can use to build agents for StarCraft. And so one application, obviously, is to have bots that can play with humans. But what's more relevant from the perspective of advancing the state of the art in AI is that a lot of these real-time strategy games pose challenges that are different from other typical tasks that are studied. And so the idea is that making progress on this will help us build tools that are more general and applicable to other applications beyond playing these games. And so with that, I hope you get a sense for what FAIR is, what its mission is, and I've tried to give you a glimpse of different projects going on individually in the vision, in the language, and in the reasoning space. And what Dhruv will talk about next are projects going on in collaboration with our students at Georgia Tech that fall at the intersection of all three.
Thanks, Devi. Hi, everyone. So what I want to tell you about is an ambitious research agenda that we've been calling A-STAR, agents that see, talk, act, and reason. And specifically, I want to give you a glimpse into 3 projects under this umbrella, the first one being something called visual dialogue. Here's the basic idea. We want to build AI agents that can understand images and automatically produce captions for them, something like a man and a woman are holding umbrellas for this picture. But not just stop there. We want to give human users the ability to ask follow-up questions, like what color is his umbrella? Notice while this may seem like a trivial task for you and me, this actually contains really interesting computer vision, interesting and challenging vision and language problems within it. The first one being co-reference resolution. Who does his refer to? His refers to that man that was mentioned a round ago. That man needs to be found in the picture so that we can talk about that umbrella, which is his umbrella, which also needs to be found in the picture, so that the agent can then answer, his umbrella is black. A follow-up question, like what about hers, is particularly tricky because it doesn't actually mention the word umbrella. The agent has to realize that her refers to that person, that woman mentioned 4 rounds ago. Hers, who needs to be found in the picture, hers refers to that umbrella that was mentioned 2 rounds ago, that also needs to be found in the picture, so that the agent can say something like, hers is multicolored. A follow-up question like how many other people are in this picture gets tricky if the agent doesn't pay attention to the word other. Because if you just focus on people, this seems like a person counting task. Run a person detector and count the number of outputs that you get in the picture. But you have to realize that because of the word other, you have to exclude those two people you've been continuing to talk about, and therefore the response only is applicable to those three other people who are in the background. And so the agent has to say something like, I think three, they are occluded. OK, so that's the task. Hopefully I've convinced you it's a challenging task. It's a legitimate question to ask, why would you want to do this? There are many reasons. The first, we think from an accessibility perspective, this kind of technology could really help users play around with and get to know more pictures that their friends are uploading on social media websites. So an agent could pop up and say, hey, your friend Peter just uploaded a picture from his vacation in Hawaii. And you could ask things like, great, is he at a beach? No, he's on a mountain, things like that. Even if you are sighted, sometimes you may be looking at something that you don't understand. So you could ask an expert tutoring system, what kind of bird is this? And it could say, this is a blue jay. How can you tell? And so on. From a pure scientific perspective, we think natural language is the most natural interface for robotics. And so we are interested in taking steps that allow users to communicate with robots in natural language. Something like, you can have an agent and you can ask it, is there smoke in any room around you? It can say things like, yes, in one room. Well, then go there. And you can give it instructions in natural language. And finally, all of us are sitting on thousands of pictures and hundreds of hours of video footage. Wouldn't it be nice if we could just walk up to a camera and ask it to find things that we're looking for? Something like, hey, did anyone enter this hallway this last week? Yes, there are that many instances logged in camera, and so on. And notice this is video or visual search, where the search is being refined iteratively through Dialog. So now that I've given you a sense of what the task is, why it's important, the next step is to build agents that can solve these problems. In order to train and test these agents, you need data sets that contain visual dialogue data. That data didn't exist, so we went out and collected it. This was collected on a crowdsourcing platform where we had two people accept our tasks. They were assigned roles of a questioner that only sees a caption of an image, something like the man is riding his bicycle on a sidewalk. And they're paired up with an answerer who sees both the caption and the picture. The questioner is asked to ask questions about the scene that they're not seeing so that they can build a mental model of this picture. And the other side responds in answers to their questions. Something like, is the man wearing a helmet? And the other side says, no, he does not have a helmet on. How old is the man? He looks around 40 years old. What color is his bike? And so on. We have, of course, recorded all of this dialogue data associated with this image. So in total, we have collected this dialogue data on 120,000 images, with one dialogue happening between pairs of workers per image, for a total of 10 rounds of question answers per dialogue, for a total of 1.2 million dialogue QA pairs. This is a really large resource that is publicly and freely available for anyone to use. Using this data, we can train models that mimic humans. That is, they try to map the input to the problem, which is images, questions, and dialogue history, to what the humans said in that exchange. We use deep learning techniques to do this, and they often work surprisingly well. Here are some examples of our models that are solving this task. This is a human-machine dialogue. So the human is asking questions, and the machine is providing responses. So in this picture, the human asks, is the bottle open? The machine says, yes. Red or white wine? Red. Any food? No. On this picture, what color is the building? Brown. What color is the clock? Black and white. Is it digital or analog clock? Analog, and so on. Notice that while these answers may be correct, we are still very far away from the kinds of long descriptive answers that humans generate in the data set. So humans say things like, what color is the dog? A light tan with a white patch that runs up to the bottom of his chest, and so on. Machines, on the other hand, are much more curt and to the point, because generating long responses is still a challenging scientific problem. It's not just that. There are some other shortcomings of our methods as well. If you ask it a question like, is the cat on the floor? The system will say yes. What is the cat on? It'll say, I can't tell. So slight paraphrases of what you're asking may lead to different answers. Here's another interesting phenomena that we observed, that for a number of questions, the system will give safe responses, like, I don't know, I can't tell. We believe the reason this happens is that such safe responses actually are valid responses to a number of questions. And so the agents discover this bias in the data set and amplify it, getting partial credit for just being safe and hedging their bets. Beyond just supervising agents to mimic humans, we have also been studying multi-agent games. Specifically, we've posed a cooperative image guessing game between two agents. One of them is called a Q-bot, one of them is called an A-bot, who have a dialogue so that one side can pick an image out of a lineup. Specifically, Q-bot asks questions, but is blindfolded, so it doesn't actually see an image. A-bot is another agent that answers questions about pictures and actually sees a target image. And they go back and forth. One side says, 2 zebras are walking around their pen at a zoo. The questioning agent says, any people in this shot? The other side responds with, no, there aren't any. Follow-up question, any other animals? No, just zebras. Are they facing each other? No, they aren't. And they go back and forth and play a visual 20 questions game, if you will. And at the end, the blindfolds come off, a pool of images is presented, and the questioner has to say, which image were we talking about? Why do we do this? Notice there's no human in the loop. We can generate, this is just self-talk or self-play. We can generate potentially infinite number of gameplays here and use that data to improve at both asking and answering questions about pictures, all without any human in the loop. Now that I've told you about those two directions that are about vision and language, I want to tell you about a third direction that pushes towards agents that take actions in virtual environments. We have recently proposed a new task called embodied question answering, where there's an agent spawned in a virtual environment and asked a question like, what color is the car? The agent has to move and intelligently navigate to find the object being talked about and then respond with the answer to that question. The thing to keep in mind, though, is while we can keep track of where the agent is on a floor plan, the agent does not have access to anything other than computer vision. So when it's asked a question like, what is to the left of the shower, the agent only perceives through an egocentric camera. This is all it sees. It has to move around, find the room that the shower might be located in, find the shower, look to its left, and then produce an answer like cabinet. We believe this sort of a task really serves as a benchmark for the kinds of AI systems that we want to develop, who have the ability, agents that have the ability to understand language. So what is the question asking me? Understand computer vision. How do you find the object how do you detect the object that is being talked about? But also active perception. You have to move to find the thing that is being talked about, and you move only through computer vision. And finally, common sense. Where is the shower located? You've never been in this house, but you've been to other houses. In order to train and test these systems, we built on top of a large publicly available data set called SunCG, which contains 3D scenes from indoor environments like apartments, buildings, and homes. And what FAIR did was to convert SunCG from a static data set into an active environment, where an agent may be spawned at various locations, tracked across locations, and fed different perceptual inputs. Of course, for our task, the agent only has access to an egocentric camera. We, behind the scenes, have access to a lot more information. We can run these experiments because this is simulation. We can run these experiments faster than real time, and we don't have to worry about safety concerns of an actual physical robot colliding into walls or into other people's, damaging itself or other people. Here are some results that I want to show you of experiments conducted in this environment. The agent is asked, in this case, a question: what room is the vase located in? This is a baseline system, walks down the hallway, stops, gives the right answer, lobby. This is our system, walks down the hallway, turns, looks at the object, and then gives the right answer. So slightly better. Both systems are doing about the same. Here's a more interesting example of a baseline system. What color is the fish tank in the living room? The baseline decides it's had enough of this experiment, finds an open doorway, makes a beeline for it, tries to get out of the environment as it can, hits boundary condition, gets thrown back into the environment, and ultimately terminated. Here's our system, much more compliant, finds the object, gives the right answer. What color is the bathtub? Here's a baseline system, gets stuck trying to make a tight turn around a corner. Here's our system, finds the object, gives the right answer. But I want to stress that there are still a lot of things to improve here. Our method and our system still suffers from a failure mode of stopping too far away from the objects of interest. So here it was asked to find the ottoman. It does actually find it, but stops too far away and gets the answer wrong. What color is the fish tank? It identifies the fish tank, moves towards it, stops too far, gets the answer wrong. Our system also gets stuck around tight corners and walls because the environment just won't let it collide into other things, won't let it proceed. Here was a tight corner that I was trying to turn around, got stuck. And here's another example where it walks and gets stuck around a tight corner. So overall, I hope what I've done is given you a sense for this exciting space of A*, agents that see, that is require computer vision to understand images and video, talk, that is are able to hold dialogue with humans or other machines, act, that is take actions in a virtual environment or make API calls, and reason, which is think about the long-term consequences of their actions and plan ahead. And I think we're really excited about the next steps in this direction. And with that, I'll hand it back to Devi.
All right, so one last thing I want to talk about very briefly before I end is to draw your attention to the fact that the directions that Dhruv talked about fall at the intersection of vision, action, reasoning, and natural language. And the reason this natural language is relevant is because we expect these agents to be interacting with other humans as they're performing these tasks. And so in a lot of these problems, it's important to keep the human-AI connection element in mind as we make progress. And so we've been doing work on trying to build agents that are more interpretable. So for example, what you see here are visualizations of where the agent is looking in the image when it's trying to answer a question. So for example, what animal is this? It shows you the region where it's looking if it were to answer the question with dog versus where it would be looking if it had to answer the question with cat. Or in the bottom example, where it thinks a green fire hydrant is versus a yellow one. And more generally, the idea being that as AI gets better, it is imperative that humans and AI will work together as a team towards certain common goals of interest. And a lot of times when we think about this human-AI team, we place the burden on the AI to have a mental model of the human. What is the human good at? What is the human bad at? What are the human's intentions and goals in this particular task, and so on. And that's certainly relevant, but I think it's also important for this team to be effective for the human to have a mental model of the AI. What are the strengths and weaknesses of the AI? When can I trust the system? When can I not trust it? And having this sort of theory of AI's mind, if you will, is likely to let these teams to be more effective as they work towards common goals of interest. And so we've been doing quite a bit of work on trying to understand how the different explanation modalities and interpretability mechanisms can help this human-AI team be more effective, or in other words, trying to bring humans and AI closer together. And so with that, we'll wrap up. If you have any feedback, we'd love to hear from you. Here's the new website for FAIR that has pointers to many of the open source resources that might be useful for you. And again, we look forward to the feedback. Thank you.
Thank you.